Okay, thank you. So, let me share my screen. Yeah, can you see my slide? Not this
Yep.
one.
Yeah.
Yeah,
Yeah.
visible.
I have a person. Yeah. So, they explained the implementation of the Edric into the 5G stack. Uh, so the contents will be like this. So, in the first place, I just showed the video of the Edric, which is implemented in the 4G stack. Then briefly explaining what is the design of the edge rig in the Fortune. Then I'll explain the 5G the emulation with the multiple UIs by using the GNU Radio, and then show some videos, and then explain the parts the where I modified in the 4G stack, the UI and the GNU Radio part, and then so I showed another demo video, which shows the edge in the 5G stack, and then I'll go through the one by one where I implemented the edge in the 5G stack. So if you have any questions, just feel free to ask me. Yeah. Yeah, this is just the video to be recorded for the rig forum. So you can see that there's the basement and then the TUAs. And then so we implemented the edge rig between the RAN and rig. And just once the UEs are attached, so we started the upper to the InnoB. Then also we ran the edge rig scheduler on the bottom part. Then edge rig scheduler switching is switching the policy, and you can see which the scheduler is running at the top. So and also the Atrik could run the PPL or with the different differently trained model. Like firstly the PPL used the initial model, but after the middle the middle the half trained model, and then finally so a fully trained model shows the better performance. Uh, so you can simply see the Etcher could change the scheduler by the sending the actions based on the observed observation from the RAM, which includes uh, the CKI and the band developer and the TX files. Uh, Here on the left side, so you can see the where we implemented the channel, the GMQ, the channel to the rig in the 4G the stack. So you can see the Mac we implemented everything the Mac layer, and then um, send collecting the metrics and then send the action to the rig, and then also the rig returns the oh sorry we collect the metrics and then send to the rig, and then rig returns the action to the band layer, and then we also use the weights received from the rig in the scheduler. Yes, the same thing I explained it's shown on the right side. So the RAN text and the RAN state, the CQI and the bank buffer, and then the RNTI and yeah TX spice, and then action is the just the weights and RNTIs. So we also use the user application the to the schedule for the scheduler. But in this case, in the 5G stack implementations, I didn't. implemented this part. Yeah. Uh, let me show you the video. The first, so I just tried to run the 5G emulation with as many as the UIs by using the GNU Radio. In the first place, that you could easily run the 5G emulation with just the GMQ GMQ channel for just one UI. But if you want to connect to multiple UIs, you have to use the GNU Radio. But when I tried to use the GNU Radio for the multiple UIs, I had some of the issues. But yeah, but first just let me show you the video and then I'll explain what I changed. Sorry. So on the left tab, so okay, sorry. Let me start the video from the beginning. On the left, the tab side, I made it the IP. I rendered the IP net NS to create the channel, the virtual the IP for the 14 the US, and then started the GNU Radio. And the GNU Radio made the throttle and all the GMQ channel. And then I restarted the opening 5GS, and then GNU Radio GNU GNOP started in the middle on the left the terminal. And then in at the center you can see the 14 US the starting. Uh, and then you can see all the IP addresses are assigned to the 14 UIs. The last UI is the dot 15. And then I started the iPro server for the 14 UIs. And then, on the right side. So I started the iPro server one by one. Then you can see all the 14 UIs can transmit receive the data. But as you can see, the spectrum efficiency was very bad. So maybe this one will be the fix someday. Uh, and then so yes, and at the first what I changed in the GNU Radio was just remove the G it, uh, is the UI part, the graphic, the UI part is so you can run just without any just UI, and also yeah you can increase any number of the UIs as many the UIs as you want. So you can just type the number of the UIs, and then Silicon Radio the made it all the source and the sync by using the GMQ the sockets. And then also I used the 11.5 the 2 uh, the threshold. And also so when I ran the 4G the stack the UIs, they directly they didn't um, I didn't attach it to the GNOP. So uh, the first I forced it to force the HUE to start with some of the delays. As you can see on the left side, I put some the delay index here. That all the UIs have its own the delay. And also, you can change the preamble so that the different preamble, the UIs which has the different preamble can be started. It can be attached to the GNOP at the same TTI. So and those are the things I made it change it. And then I was able to run the 14 the UI, the emulation. And then so far, so do you have any questions? Can I get going? Okay.
I have a question.
Yes.
So could you go to slide 4? No, 6, please.
6. Yeah.
I don't understand the relation between GNU Radio and SRS runs. So this GNU Radio just doing a splitter or something? What this GNU
The GNU
Radio is
Radio.
doing? Yeah.
Actually, when you run, when you use just okay, so GNU Radio just connect to the GNOB and the UE by using the GMQ the channel. Just it create the GMQ channel between
Just a
the
connection.
GNOB.
Okay. Mm.
Yeah, and
And
then you can
GNB
also
and UE implemented with SRS run. Is it correct?
yeah, that's true. Yes,
Okay,
yes,
okay, okay.
that's correct.
Okay. Yeah. I
Yeah,
understand.
and just GNU
So
Radio.
it's just for
Yeah,
IQ
yes,
streaming, right? I think he's using GNU Radio to do the IQ streaming and multiplexing, right? Okay.
I see.
yeah.
Okay.
Essentially, one way you have to copy all of it to all the UEs. The other way you have to add them up and give it back. Right?
Yeah, here.
So from the G0B to UEs, you need copies to go to all the UEs. From UE back to G0B, you need to sum them up and give it to G0B.
I see. Yeah, thank you. I understand.
Okay, thank you.
So you will go over the detailed code base and how it's structured, or you already have gone through that?
Yes, Professor. So maybe after the
Sounds good. Continue. Yeah.
Yeah,
Go with
I
your
think
flow. Yeah.
that okay. So maybe this is the video. Maybe I can show you the. Yeah, maybe I can show you the how run yeah the entry in the 5G stack terminal. So just I split it the terminal for the each part is here. First, so I had some issues with the 5GS Open 5GS when I ran the 5 SRS ran the 5G stack. Uh, so I decided to use just the source. I decided to compile the source and then to run the open 5G ads. So then maybe it will help us to modify the open 5G ads to someday if we need. And then also here I run the GNU Radio for the 3 UI. So you can see the GNU Radio created all the GMQ, the source and the sink and the throttle. And then I run the GNOB for the emulation. And then you hear. So I run the UIs. So once the UIs are attached to the GNU Radio, GNOB, you can see that they are assigned. Okay, the IPs are assigned to the UI. And then I start with the iPerf. I started the iPerf server for UI 1, 2, and 3. And then here iPerf client for the UI 1, UI 2, and this one's UI 3. So so far I just ran the SRS ran and the iPerf, so you can see the default scheduler is the round robin. You can see this all UIs have similar throughput. Then on the top right terminal, I start run the rig part. You can see the rig receives the metrics. Here the RNTIs and then the CQI value, and also you can see the weights assigned it to the RNTI here.
Then are you
So
running a CQI trace here or it's fixed CQIs?
they are the same, just 15 CQIs. So
Okay, all
I didn't.
I see. Okay,
Yeah.
cool.
So you mean the CQI, the emulation
Correct.
part
Exactly.
we
And right now
implemented
it's
in
15 on. Okay, good.
Oh yeah, I haven't changed it yet. So maybe I'll make modification in the CQI channel part also.
Cool.
And you can see that the UE1 has the weights, the point to the 1.3. The UE2 has point to 5.3, and the UE3 has the point to 3.3. So you can see the UE1 has the lowest the throughput. The UE2 has the max, the highest one.
And
Then,
sound as well. It shows the CPU is
yeah.
pushed.
So so yeah, when I stop the HX, you can also see the order the UE recover is the throughput.
Wohyun, are you running this on OAI box or a laptop?
I'm running the laptop. Just I'm running the same laptop.
Okay, no wonder. So it's running Zoom and everything else. Okay.
Yes, Professor.
Okay. Okay.
And also, I think that one of uh, the issues we had when we ran the emulation was the GNU Radio, because the GNU Radio used the graphic, the UI. It was unnecessary, but whenever we started the GNU Radio, yeah, it used about 300, 200 the CPU. I think it's after removing the graphic UI, I think it's the computation burden was lessened.
I see. That's good to know. That's good to know. Cool.
Yeah,
I
so
mean,
I
the
think
UI is
that,
irrelevant after all, as far as no radio is concerned. Yeah. Cool.
yeah, we don't need any the UI, so but yeah, maybe and so you can run the 5G stack on your machines, so it doesn't require any the high performance. Okay,
Of
so
course,
let
your
me go
laptop
back.
is running its fan quite loudly. But yeah.
Yeah, yeah. That's yeah. Let me go back to the. Uh, so yeah, so from now on, so I'll try to go through the code, so where I implemented the one by one. So there are four parts in the RAN stack. I implemented in the RAN stack. The first one is the collecting the RAN state. The second is the send the RAN the state from the RAN to rig. And then the third one is receiving the weight, and then the last one is using the weights in the scheduler of the RAN. And then in the middle, I just briefly go through the rig implementation. The first, so as I mentioned before, so we implemented the edge rig, the channel in the Mac.cc, but in the 5G stack, there was not the Mac.cc. So there was the many the changes in the code and the structure, and then I tried to find the which function is was called the every TTI. Then I found that this is the run the slot function in the cell schedule that CPP. This function called the every TTI. And then you can also see the uh, yeah TTI index. So here, yeah, this is the scheduler that CPP, and then this is the function the code at every TTI, and then yeah, this is the parameter is the index, the TTI index. So this one, TTI index is the shared for all the modules, and then you can see the modules are run. This
Wohyun, sorry, can you give me the variable name for the TTI index? SL dot no TX count.
yeah, SL underscore the TX, Professor.
I see.
SL underscore the TX.
Cool. And so
The
that
slot.
is what we sync with. Question
Yeah,
I
yes, yeah.
in this context. Now, if you think about it, the TTI index updates every millisecond, right? Every slot, basically, right?
Yes.
So it's
Yes.
like slot thing. But how big is it? How many slots will it run before it overflows and resets? Is it a
Yeah,
long integer? What is it?
Oh, actually, I think I remember the maximum number of the theta index in the 4G was the not the big. The several, I think the 10,000 or something like that. But I'm not sure. But the 5G stack has the bigger number in the theta, yeah, index,
So
the slot
whenever we
index.
do sync and things like that, we do it modulo the size, is it?
In the 4G implementation.
4G or 5G, basically the reason is at some point it will run out and it'll over, kind of
Yeah.
uh,
Yes.
right, it'll start at zero again, right?
Yeah, that's true. Yeah. Yes,
So in other
Professor.
words, all the arithmetic involving the TTI index needs to be done modulo the maximum, right?
Yes, Professor. Yeah, let me try to find the maximum number.
Okay.
But give me a second. Maybe you can see
The reason I'm saying this is the RIC is supposed to provide control info for the next TTI, typically. Although we could choose any number of TTIs ahead, typically we are providing next TTI, right? So what
Yes.
is next TTI depends on modulo, right? In other words, if it is gone to the largest number, the next TTI is zero, not
Yeah,
whatever.
that's true. Yeah.
That's what I'm saying. So we have to be a
Yes.
little cautious there. Yeah.
Yeah, maybe so I can check the maximum number of the slot index. But in this case, you can see the here this the 972 is the slot index. Then you can see here you see the one was the is decreased by one,
Mm-hmm.
and then okay, so
And six,
yeah, maybe
what does the end of one
uh,
slot mean? It's where you ended it.
it just that I printed out the sentence in the function
Okay.
I was tracking. So yeah, it doesn't mean anything.
Okay.
Just print out.
I see.
Yeah. Just I want to see the boundary between the slot, so that's why I printed out
I see.
here. So okay, so yeah, I checked the maximum
Check
number
what
of
it
the
is, and
slide.
we should make sure that we are accounting for that in our arithmetic, basically.
Yes, Professor. So it's a good point, Professor. And then okay, so okay, yeah, this is the yeah. So maybe in the future, so we could discuss which design would be the better, because the I just chose this function, so it's because I just found, and maybe somebody can find the better place to implement the HV channel, and then also I implemented uh, the real-time E2 channel function here. So this function is called the every TTI, and then inside this function send the metrics and then receive the weights. So then okay, maybe I can go. Yeah, let me go to uh, the place where we collect the state. So let me go to the line 177. So 177 here. Yeah, this is function. So I was able to collect them all the matrix information. So this push it result, uh, inside the push the result, you can see the report matrix function, and then inside the report matrix you can see the compute report. So each UE compute is the own the all the states. So inside the compute the report you can see all the information, the metric information per the UE, such as the RNTI, the CQI, the RI, and there you can see the DLUL, the MSS, the bit rates, the downlink, the uplink. So I could find all the information here except the backdoor buffer. So maybe uh, I show it where I get the backdoor buffer later. Then just okay, in this case, so the collecting I was able so it missed this matrix the instance can be used to get the matrix information which we need to send to rig. So and then go to the yeah sorry, so I go to the lines where we can get the backdoor buffer. So okay, here, yeah, this is the line. So we could start with the max cell, the processor, the CPP line, the 79 to here, the line 79. Here, this function and called the handle slot indication implementation. And then inside here, so one, so line. Yeah, also the channel get state. Yes, sorry, it's 9197. Yes. Here's this function and the course to another function to get the okay here. Inside the functions, you can see the backdoor buffer value is to here. Yeah. So this function to returns the backdoor buffer up for the each UE. So you can see that I print out the RNTI and is the backdoor buffer size. So now eventually I need to pull this information into the where I implemented the real-time channel, and then this the value will be will belong to the message to the rig. So okay, yeah, so I ran through the metrics and the backdoor buffer where to collect the metrics and the backdoor buffer in the run side. Then yeah, just I showed where I sent the run state to the rig. Okay. So inside the real-time it function, yes. So the sending the matrix is implemented in the later part, in the later part of the real-time it function, because so because the rig has the blocking call receive function, so without the sending metrics to the rigs, there's no the communication between the no the E2 channel is activated here. Okay. Sorry. So, yeah, here. So from here, so we send the metrics. So the first is just we get this matrix, the instance, and they get the RNTI and the CQI. And here I just send the DLMCS inside of the payload buffer. And also I was I sent the download bitrate. So and then
Ushasi
yeah.
and I were discussing this today. We were wondering or thinking about how we should kind of develop these message structures with the notion of service models. So, in other words,
Yes.
we want what are the two? We want a report type message and we want a policy type message. So, in other words, at the RAN side, we need the ability to create essentially some class called report message class, and then we can extend it for whatever we want. So the basic message class, the message objects can have things like RNTI, CQI, buffer state, say. And if somebody wants to extend to other things, they can extend it and add other fields. So they can have subclasses of it. And at the RIC side, we want an E2, real-time E2 policy message class, right? Which currently is
Yeah.
going to send RNTIs and weights as a message object, right?
Yes.
But if people want to extend it, they can send other things like if we're doing beam selection or MCS selection and things like that, they can extend the class and increase it. Specifically, Ushasi was working with your current message and she expanded it to also include uplink related stuff. And I was discussing with her because she's not actually using the downlink stuff. So it's not useful, right? And it's just sending it for no reason. So in other
Yeah.
words, if we have the ability to define, as I said, our real-time E2 report class and policy class at RAN and RIC respectively, and we extend them as we please, it might make it more flexible for different applications.
Yes, Professor. I think it's a good idea. Yes, Professor. So yeah, I tried to make the report class and the policy class. Yeah, policy class.
That's the E2
Yeah.
language. That's why I was calling it report and
Yeah,
policy.
yes. I think yeah, we'd better follow you comply the standard. So yeah, by
It's
the name
kind
again.
of complying, but yeah, at least it
Yeah.
has the same feel to it. Yeah.
The same name. Yeah. So yeah, I think it's a good idea. It also looked better. Yeah, than this just the hard coding part.
Right,
But
exactly.
yeah, that's true. That's true, Professor. So yeah, I think about it, Professor.
Thanks.
So yeah, this first just the wrapping the message and then send the message. This the message by through the just okay. Yeah, here. Just publish it. Jenkins publish send this message to
So let me maybe take a pause here, right? Okay. Everybody is finding this useful.
Yes,
I
for
am,
me.
Matt.
Okay. So let us, yeah, okay, keep going. Yeah.
yes, Professor.
Anyone
So,
has a different comment, like you want Wuyun to focus on something else, maybe at this point, right? Like go in more details of this or like less details of that. Either ways, right now the feedback is welcome. And Wuyun, I want to remind you only have 20 minutes, right? So I want to maybe like see, I don't know if maybe we can cover the entire thing today, right? If not, we'll maybe go on the next lecture as well, right? Sorry, not next.
yeah, I think
What am I saying?
yeah, maybe it's almost done. So maybe it's
Sounds good.
3 parts can be yeah the winter so I can go through the two more parts. So okay, here and then maybe I can briefly go to the rig part. The rig also the PPO gym the environment, and but in this case we could just change the scheduler by to change the select the algorithm index here. If the index algorithm index 1, so you can start the max CQI. So algorithm index 2, the proportional the fairness algorithm is used to the calculate the weights. Then also when the index is the 7, we could use the PPM model. So when I go into the, for example, the max CKI, inside it, so the first it gets the matrix from the a matrix, it gets matrix from the message the RAN sent. Here you can see just it parts the message once it receives the, okay, here once it receives the message through the GMQ channel. So as I mentioned, this blocking call, the rig always waits the RAN for RAN to send the metrics to itself, and then the parse and then get the RNTIs and the CKI, and then yes, the backload buffer and some other values, and then once it gets all the metrics, it calculates the weights per the RNTI. So in this case, we use this algorithm, the max CKI. So it then finds the which the RNTI has the maximum the CKI, and then give all the weights, and then the calculated the weights are returned, and then the calculated weights pairs of the RNTI weights are sent to the RAN. So here you can see just the weight, the RNTI and weights are wrapped in the message and sent to the RAN through the GMQ socket. Then
This is Rama from UCSD. I have a question regarding the choice of ZMQ. So, is the ZMQ transport something that's integral to EdgeRig, or does it support other kinds of transport as well?
oh, sorry, what do you mean the support?
So basically, the reason for ZMQ is it's already there in SRS codebase. It's all the libraries are already integrated, so it saves us. I mean, EdgeRig is in some sense compatible with any PubSub regime, right? All we're doing is publishing stuff from. There's two PubSubs going on, right? The RAN is publishing stuff, and the RIC is absorbing it in a blocking manner. And the RIC is publishing stuff, and the RAN is absorbing it in a non-blocking manner. ZMQ supports both, right? So, and furthermore, one other nice thing about ZMQ is it natively supports something called conflate, which is last in, first out. In other words, from RAN to RIC, we want the latest info just in case any kind of delay has been seen. I want the latest TTI from the RAN so that the RIC can sync up to it. So ZMQ has a so-called conflate option, which is essentially last in, first out, right? So all these are natively available, hence ZMQ.
What about, so whenever I use ZMQ, I've gone into some weird regimes where in PubSub, if you can't keep up on the subscriber end, ZMQ will arbitrarily start buffering to a large amount and these kind of things. Have you guys seen?
So that's the conflate option.
Conflate takes care of it. Yeah.
That's the conflate option.
That's the last in, first out.
So you discard everything and you just keep the last one which is there.
The socket option that I can set?
Yes. It's once you select subpub, and then you have to, in the subscribe mode, you have to use conflate equals to 1.
Oh, okay. Thank you so much. This is something that I learned new today.
So that was very useful to us. In fact, it was critical to us because indeed it was horrible. It wouldn't.
Yeah. I mean, I had to replace all my PubSubs with RepReg because I didn't know this thing existed. But I'll definitely go check this out right now. Thank you so much.
It saved our whole, exactly. Because now we don't, and because we have the TTI index, we know which is the latest TTI as far as the RAN is concerned, and we pull EdgeRig to kind of catch up, essentially.
Is that why this max TTI discussion was also happening, because that can wrap around, or no?
Yes, because when it subscribes, it says, okay, this is the current TTI, and EdgeRIC is supposed to send info pertaining to the next TTI so that it can use it, right? So therefore, I need to know which TTI is current and which TTI is next.
Okay,
But
got
if
it.
next is a wraparound, it needs to know that the next one is a wraparound TTI.
Got it. Okay, yeah, thanks so much.
Even if we don't do that, if it fails, it will fail one slot, then it will catch up again next time.
Yeah.
Right.
So for ZMQ PubSub, I can also add on the publishing on the subscribing end. If to handle a issue of slow case, you can use the polling option as well. If it does not receive something in that time, it simply moves on with its execution.
Right,
So
but
these,
so the polling has a timeout, right? And that timeout has
yeah.
latency. So those are the kind of things.
So polling helps you with the non-blocking option. Like the program doesn't stop if you do not receive something.
But still, the polling has a timeout, right, Ushashi? And that might be the minimum timeout is like 1 millisecond.
Yeah. That
So
is
it will
there.
block for 1 millisecond. It's not.
No, you can. I did it for less than 1 millisecond. You can do in the microseconds level.
I see.
Yeah.
Interesting. So is this the C or C++?
This is the we use it in the Python ZMQ of the Python library.
I see. Okay, we'll take a look. Thank you.
So some other folks asked us, how about SCTP, etc. ZMQ is compatible with UDP and TCP. It looks like there are some forks for SCTP, right? I've seen a few things which say SCTP, ZMQ, etc. But as of now, we're using IPC basically because both of the processes are running on the same. So it's just ZMQ with IPC.
Right. It's like similar. Is it similar to domain sockets underneath? That's
probably. I don't know what ZMQ is doing under the hood, but very likely it's using Unix domain sockets with IPC.
Claiming TCP underneath. That is what I understand. So it's still doing TCP over IPC.
It could be. I don't know what it's doing. It's low latency.
But I'm a big fan of ZMQ. I just this PubSub pattern. I didn't know it had this conflate option, so I'll definitely check that out.
So, but I do hate PubSub for following reason the ZMQ, right? Because it's sort of not good for high throughput things, right?
So that's what I'm trying to fix, Dinesh. When for the thing that I am doing, I'm trying to run this in high throughput, and these kind of things are bothering me. Like microsecond level latencies are annoying for me.
So I think the better way in that case is doing some using ISCTL libraries or like shared memory type of things, right? Like I think isn't that better way of doing?
That's a good point. If you want to do a lot of IQ data, high throughput stuff, like what Wuhan is up to is fairly low throughput. It's just state info going one way, coming the other way, right? But if you want to grab a whole bunch of IQ and do some real time processing, then I agree. You do need a high throughput solution, right? Actually, that's why I'm saying this. This is very E2 like. Both our application and our requirements are very much like E2, except that we want synchronization, right? So indeed, if the regular E2 had the synchronization as part of the protocol, we wouldn't have to invent our own, right? So it's awfully like E2, except we've added on this thing, right? And therefore, it also has these, in some sense, the application kind of which can be supported are also E2-like applications, which means state reception every now and then, control every now and then, which means again once every TTI, not a whole lot of stuff is going back and forth, right? Anyway, you can please continue.
Yes, Professor.
So maybe just one small follow-up like on this. So what do you think is the, like, since you're telling that ZMQ is not very good for high throughput, SRS Run does use ZMQ to stream IQ in the simulation mode, right?
You're right. Maybe I'm wrong.
So I will maybe I don't want to derail the conversation, but there is a slight difference between large number of messages per second and high throughput. So ZMQ can do many gigabytes per second, but sending many messages per second is hard. Like you can't do many small set of samples many times. You can do large set of samples lower number of times, get high throughput. So these things you'll have to split hairs when you get to high throughput regime. Yeah.
So have you or like anyone done some study on what's the maximum bandwidth IQ data that
Yes.
ZMQ is able to support?
Yes, Agrim. I have all the answers to your questions. We can talk, yeah, later.
Okay, yeah, sure. I can
So
message
actually,
you.
Ish, very quick high level thing. So can you actually do then using ZMQ? Actually, it is happening, right? Using ZMQ, the IQ data is coming from UE to RAN and it's being processed in real time. So it is potentially feasible then to process
Yeah.
IQ in real time via ZMQ stream, right?
Yes, it's
Yeah.
possible. Yes,
So
it's
it is
possible.
being done.
We have done 100 plus mega samples per second on ZMQ. It's possible.
100 plus mega sample would correspond to how much bandwidth?
100 megahertz of bandwidth.
Okay,
Or, I
right.
mean, in LTE regime,
that
yeah, we
would
can
depend
do
on-
100 megahertz of bandwidth. On server class CPUs, on laptop class CPUs, you can do higher because their single core speeds are faster.
I see. That's interesting because I mean, what Vujan showed is 20 megahertz or 10 megahertz typically. So we are not
Yeah.
stressing out the MQ at all. But it's going through that GNU radio block as well, in terms
Oh
of.
yeah, GNU radio block. Yeah, that's
I
true.
wouldn't trust GNU radio, but raw ZMQ is very good.
Nice.
GNU radio is not very good.
Okay. Interesting.
Yes, let me go through the rest of the parts. So yeah, once the RAN receives the message from the rigs, it just parse the message and get the RNTIs and the weights. And then the most important part is to transfer the weights to the scheduler part. So yeah, the scheduler. Okay. Yeah, the scheduler is implemented. Okay, the first is that I made it the function here. Okay, so the scheduler I made it just a set weights function to store the received weights inside the UE scheduler the class. So here. Okay. And then once it saved this weights into in the underscore the weights the variable, then when go to the scheduler, the time the RCC, and then 86. So yeah, so here's when the downlink allocation. 308. Oh, sorry. Yeah, 165. So, yeah. So here's this is parts where the PRBs are located based on the weights. This weights has has something inside. So if the weight is has the node that has the node data, so the deport the scheduler just ran the round robin, and when the run receives the weights from the rig, so you can see just get the weights per the RNTI, and then just allocate the number of the PRBs per each UI. You can see here. So in this case, the 10 megahertz the bandwidth. So the total number of the MPRBs was the 52. This is the hard recorded. Maybe so we could use some the better way. And then so this is the final the variables which will be which is used by the scheduler. And then as you saw the videos, so all the the PRs are the use the based on the weights. So I think that's all. Yeah. Okay. Yeah. So I prepared for the, to this meeting. So is there anything? Do you have is there any questions or anything you want
Have you done
me
any
to
CPU
explain?
profiling of the code that you have written? Like how much overhead does it add over the normal operation? Like CPU utilization
The
or something.
you mean the due to the Azure implementation?
Yeah.
I haven't checked, but I don't think it's much because the just
I can answer
yeah.
the question.
So yeah,
Okay.
spectral efficiency is same. Shasi.
Yeah, so for computational overhead, like running EdgeRig and SRS run is like somewhere like 20% more than just vanilla SRS run.
Okay.
Incidentally, how much compute overhead depends on the size of models you're running. So for the RL inference stuff that we were doing, it was 20% more. You do some enormous model, it'll take more, right? And if you do something much less, such as just KPI streaming, it'll take even less, right? So it depends
Yeah,
on what
like
you're trying to do with EdgeRig, that compute.
that's a good point you mentioned, because I was seeing some like papers they are doing like RL for energy efficient scheduling, and the RL algorithm saves like 10% of the power, but
Right.
then it's going to consume 20% by itself, right? So
Right.
I mean that's something you need to do then.
We have to, yeah. Incidentally, we are now working with smaller models. Ushasi, remember that 20% was with the model with NSDI, which was more, it was more comprehensive. Now I don't know, it might be
But
more.
we are doing that 10 times.
Yeah, the index stuff has to be run for each. I don't know. It depends on what you do, basically.
No, it
But as
depends
far
on the
as
metric,
the
right? If it's improving throughput and stalls, then it's a fair trade-off. But like if people are arguing that we improved energy efficiency and they didn't take into account how much energy or this thing consumed, the RL thing, then
compute itself,
it's a done
although
deal,
I
right?
don't know. There is this question of energy efficiency is in terms of transmit power and stuff like that, right? So it's not clear that the compute and the over the air transmit power and things
Yeah,
like that
that's also a good point. I mean,
comparable.
there's some correlation. Yeah, like then really you need to compare in watts. Like people usually report these savings in terms of percentage of how much it was earlier. So yeah, in terms of watts, then it will be a
Watts to
fair
watts to watts. That's fair, right?
watts to watts. Yeah, yep.
Right, specifically, if I turn off all transmission, it'll save, I don't know, it depends on what kind of power amplifiers and stuff you have. It'll save quite a lot, I guess, right?
Mhm.
And my compute may be nowhere near that kind of number. So who knows? Yeah, it's put to measure. The other thing you asked was the efficiency or the overhead of our code sitting in there. We
Yeah,
found that the spectral efficiency was essentially identical. So in other words, whether we run a scheduler or whatever in the stack versus on EdgeRig, it was essentially showing no difference because the number of EdgeRig lines of code inside the stack are fairly small, which
Yeah.
Uyun was super
Just,
careful because we don't want to break
yeah.
it.
Yeah. That's true. Just with several the less than the 200 lines. So I don't think it's too much.
So it
The
seems to
overhead.
run pretty much with the same efficiency as the original SRS ran code.
Yeah, but only just the rig part will require some, yeah, gives them the computation burden. But
So if
I
you give
think
one more core to run the rig, you're in good shape.
yeah, yeah, that's true. Yeah, I think it's a good option. Yeah. So we can use the GMQ, yeah, as the TCP or the UDP. Yeah, that's true. So yeah, we can definitely. So maybe say in the future we are trying to run the multi-DRAM for the one the rig. Then in the case that we will definitely use the UDP or the TCP, the GMQ. Yeah.
Actually, Ushasi, in your multi-run, she actually is running it. Are you running all the RANs on the same machine, Shashi, or are they on two machines?
They're in the same machine.
Right now they're in the same machine. Multiple.
Yeah.
Okay, nice. So you just stick in two radios into the same machine, is it?
I am doing it right, not with
Oh, right now it's
radios.
emulation. Okay, so it doesn't matter. But yeah, I guess it is feasible, right? You just use two radios, you put them into the same machine, you will have two RANs.
I haven't tested that.
Okay.
Yeah, I think that's all from my side. Yeah, thank you for your time.
Sounds good. Any other questions, thoughts? Everybody wants to go into more details of one specific thing, right? Anything, anybody has a request for Wuyun on SRS RAN?
Yeah, see, if you want to run the Edgerix stack, the 5G Edgerix stack, just let me know so I can share the code or so. Yeah, eventually I'll try to make the Docker version of the 5G Edgerix. Yeah.
Actually, yeah, if you could post it in the 5G channel or something, some README that we can just set up and run, that'll be great.
Yeah, so Wuyun, the next steps are on the GitHub, right? We have a GitHub for this particular discussion, right? On that, if you can put down your instructions, your files, and your code, right? Okay, and how you run it, right? I think that would be great. Okay.
Yeah, maybe I can upload the how to run the entire
So-
setups by the video. Yeah, I also can upload the video.
So
Showing
put
the- all
everything
the-
which
yes.
everybody should be doing, right? Like for example, you can link to different repositories and put down instruction on how to create, right, a markdown file of sorts, right? Okay. And of course, these slides and everything else, right? Okay.
Yeah, sure.
So same goes for Saru and others who have done previous demonstrations. I was looking at some time back, right? I think we still like are missing a few details, right? Like Surya, I don't know if Surya is here. Okay. Okay. All right. Anything else, anyone? Any recommendations? Anybody wants to learn more about SRS RAN in a specific direction or dimension? Ish, Agrim, William, anyone?
Yes, so
Just maybe if we were on this, oh, sorry, go on.
yeah, so the main thing to know is like how to modify it for like different applications. Like I think the main thing, like even what we learned from Beam Armor is like understanding the code base to figure out what are the things from RAN we need to pass it to the rig. So here with Edgerix, we have more parameters in terms of the CQI, user index, RNTI that we can pass. So in a way, most of the time, for example, if you're doing beamforming in millimeter wave, we need some SSB or other kind of signaling. So exactly like how we package that into this framework. I mean, this is not standard compliant yet, but it's still like some way of like packaging some new information from RAN, like which is there across multiple files in RAN and pass it to the rig. So some kind of framework, like how exactly we'll go ahead with such thing would help.
Right. So actually, Ish and I guess Surya is not here. In terms of kind of integration with OAI stack and things like that, this issue will come up, right? Because we want to keep the Edgerix portion more or less the same, while we want to create effectively a similar agent in the OAI stack to allow SSB passing, and also when we're doing beamforming or beam selection, you want the beam selections to come. Well, I guess the beam selection could go directly from Edgerix to the FPGA, right? It need not go through the RAN stack. Is that correct?
Yeah.
Because you'll pull the state info, SSPH, etc., from the RAN, and the RIC will decide, okay, this is the next beam to be chosen, send that to the FPGA at the phased array end, and then the phased array, when the next TTI happens, will load that particular, or will utilize that particular beam. So in fact, this TTI sync will be helpful there also, because what you will load is the beam appropriate to the next TTI, right?
And I think we have to ensure that there is no two levels of control. Like should not be controlling the beam along with the RAN also. So like you might have conflicting cases where RAN assigns a beam, but Rick wants to override that beam or something like that.
Correct. Right now, I think the OAI RAN has no ability to choose it, right? So if it does have the ability to choose it, then it's even better because then Edgeric can just tell that module which beam it wants. Like that's what we do with the scheduler, right? We don't write our own scheduler. We write the scheduling algorithm, which says, you know, this guy gets so many weights or blanking,
Yeah.
whatever it might be. And it is sent to the appropriate module inside the RAN, which does the actual scheduling, right?
Yes.
So we don't, we effectively override it by virtue of, you know, our agent sitting there at the right place, right? Bhujan, you're saying something?
Yeah, I think that I agree with you. Yes, Professor. Yes.
So,
that's
so Surya, if indeed there is the ability to choose the beams inside the RAN, very good, right? We would rather do it that way than do it, you know, out of band, right? But I don't think it's there currently.
Yeah, so I think it's a good motivation for Rick, like a functionality like this, which require interface with external hardware and phase array could be like different for different vendors. They Rick makes much more sense than making it as a protocol in band itself.
And if you want to choose your own beam, you know, beam steering algorithm, it is much easier to kind of just put your algorithm in and see what happens, as opposed to modifying the RAN stack every time, and you know, you might break something in there.
Just
Right.
like for scheduling, we figure out a way for control messages, which should be the weights.
Correct.
Beam hopping, we need to figure out exactly what the control would look like. Will it be something that, as you said, Rick, directly interface with the FPGA, or will it be something of the form of a control message that goes to the RAN and RAN updates some of its protocol or configuration based on the control message from the Rick? So in a way, I think this itself need some kind of thought, like about the implementation, which goes in a way with ORAN compliance to some sense, like will it be some kind of ORAN standard compliance or not in terms of
Right.
what messages can be passed and what not.
One thing is for simplicity and essentially robustness, you might want to start by putting the entire beam selection part in Edgeric so that you know that you have not messed up the OAI stack in any manner, right? And once you're comfortable with what it's doing, you can just pull up the portion which is actually doing the beam selection and writing a module. Well, it'll have to go from Python to C++, I guess. But you'll have to write a little module which sits inside the OAI stack, but if you think about it, that module in the OAI stack has to interface with that FPGA, same FPGA, right? As Edgeric would do, right? Like in the IBM arrays, it's a Ethernet cable between the phased array and the host computer, which takes this control messages. And in your case, you said it's something similar, right? How do you decide which beam is going to be chosen next?
Yeah, right now it's a computer program that decides. We have MATLAB or Python-based code which assigns the next beam.
Right. So easiest thing is to put that inside Edgeric, right?
Yeah.
Then you're done, right? But if you want to do that within the OAI stack, you'll have to rewrite it so that it will run in there, and you have to make sure that it doesn't break any timing, etc. And call that module every time. And of course, Edgeric can say, if you want it to do, which beam to select next based on an algorithm, right?
So, yeah, one of the challenge, like similar to Edgeric and all, is understanding the lines of code in SRS RAN to figure out where the 3GPP compliance structure is there, like where this SSP feedback is coming from the user, which gives feedback of which beam is the best for the user. That has to be passed to the RIC to make the
Correct.
information is something like which is quite hidden right now in the code base.
I see. So when you said you have your Python code which chooses the beam, right now it is quote unquote blind. It doesn't have that feedback.
Oh, it is, we are not using any SRS RAN or OAI. It is our own custom thing, everything, which is only a file layer functionality.
And
There,
so that provides that feedback.
yeah, there we have explicitly had our own non-3GPP method to implement this.
I see. Well, I don't know. In OAI, if it doesn't exist, you might have to do that to make it work, basically.
Right. Okay. I
Anyway.
think Agam had one thing we can then conclude. Agam,
I
you
think more or less you covered, like I was about to ask this kind of the same thing.
Yeah, so basically for building any new application, this is the pipeline. In the way, first figure out the part of the code in SRS RAN where you can put this uh, report, which will be GMQ will send that data to the RIG, and then RIG would be Python-based end-to-end code, which either directly interface with FPGA or external thing, or send a control message back to them.
So
One thing maybe Ish I had on this, right? Like I agree with whatever you discussed. One thing I wanted to know more: would this pipeline remain the same if you do with OAI instead of SRS RAN?
it should be awfully similar, right? Wuhan chose the Mac, the scheduler module, because it is indeed called once per TTI, and we wanted this TTI by TTI sync, right? So to add to Isha's comment, right now we were kind of thinking that okay, our agent will live only there, and it'll pick up whatever variables we want. If indeed we want MCS, etc., we'll bring it in that location, and then from there feed it to wherever it needs to go, right? So in other words, we don't put our agents all over the place. We keep it only in a single location for the report and the policy to come back, right? And that we chose as the Mac module because it is called once per TTI. William?
Yes, Professor. Yeah, that's true. So we try to the look for the place where we get the metrics information, and then so the where we could easily transfer the weights for to the scheduler. Maybe it's that is the first we better define the which function is called the every TTI, and then the where the collect the metrics the information you want to collect. Yeah, that is the starting position. Yeah.
So one thing, have you looked into OAI, and do we understand what kind of scheduler is currently implemented, or what is the status in OAI?
No, I haven't.
We're
I
hoping you
haven't.
can teach us OAI.
Yeah, any. Yeah,
Okay.
I haven't seen any OAI code yet. So
Okay. Yeah. I think that would be the next step to see and migrate this from SRS to OAI and see if we are still getting similar performance, or how does it matter across multiple stacks.
Right.
okay.
Personally, I think it'll be a question of finding out where that scheduler is. Again, if we want to replicate, we'd have to go through it and find the scheduler module and see if it is similar, and kind of insert our EdgeRic agent in there. But the actual Python EdgeRic code will be essentially unaltered, right? Because as long as we retain the same message structure, and of course, this question of ZMQ will come in because does OAI natively support ZMQ? I'm not sure. SRS, it turned out that it did because they use it for their emulation stuff. So it was nice for us. But
Yeah.
if it doesn't, OAI doesn't support a messaging system, we'll have to add it in. That will cause a lot of overhead generally. Because I remember early on, we were thinking of using Redis as our messaging. And one, the overhead was high, and two, it was a little flaky sometimes, right? So we luckily we found that SRS was in there anyway, so we stopped using Redis for the messaging, which, as I said, anyway was a bit slow because Redis first writes to memory, then pulls it out and does something weird, right? So it was a little too slow for what we wanted. So we'll have to see what kind of messaging is appropriate for OAI.
So is there a GitHub already there, or is it something ongoing work? Like, can we look into it right now?
4G is already up. We shall see there's a link in the NSDI paper. 5G is not yet up. So if you want to look at the 4G version and try it out, it's there already.
Yeah, so like the one Wohin you just presented, like all the functions that we can test it ourselves.
Yeah, the initial part of his presentation, he was talking about the 4G version. That is there.
Yeah,
5G version is almost ready. You wait a little while where we can update the 5G also, I guess. But 4G
yeah,
is ready.
maybe after the implementing the secret emulation and also the pulling the backup buffer, then yeah, it can be downloaded in GitHub. Yeah, I'll let you know. Yeah, once I upload it.
Okay. And just on a related question, like migrating from 4G to 5G, was it very similar interface, or was it like hard to do? Like how things has changed from 4G to 5G within SIS-RAN for your purpose?
Actually, the structure of the 5G was different from the 4G, so it was hard for me to find the similar functionalities in the 5G to the 4G functionalities. But yeah, just I was trying to track the functions, and then it didn't take much time. Yeah, but yeah.
I heard that maybe it was Dinesh who told me, maybe it was someone else, that SRS got a big grant from DoD, and they had a bunch of good software engineers using that. So their 5G stack was much better engineered than their 4G stack. I think Wohin also liked the 5G.
Yeah, yes, Professor. Yes, when I see the 5G stack, so it looked very organized and then very modularized. So yeah, looked much better than the 4G. Yeah, that's true. Yes, Professor.
Okay, so it is good to understand 5G structure, might be more easier. So reason I'm asking is now we are migrating our beam armor code, which we implemented with 4G SRS-RAN using GMQ and all. And migrating, so what it does is basically it sends the raw IQ sample from SRS-RAN to the HDIC, for example. And yeah, getting, and we want it for each antenna in a multi-MIMO system. So basically 5G has a slightly different data structure, and it is a bit harder for us to understand. Like maybe over time we would understand it better, but in a way, like getting MIMO IQ samples for each antenna, that is something we are looking for, like where we will find this information and pass it to the. So yeah, I will share more detail like when we have more success. But yeah, just wanted to know how 5G working with 5G or moving from 4G to 5G is in general.
Yeah. Once you get used to the code, so yeah, maybe it won't be hard. Yeah, I think.
Okay, thank you.
You're welcome.
Okay, I mean, if there are not any more questions, we can conclude it. I think Dinesh would have left for his class.
Thanks, Fuhyun.
Very good. Thank you.
Thank you.
Thank you.
you.